Gradient Penalty GAN Framework for High-Fidelity Fingerprint Synthesis, presented by Alexander Stryuk and Yuri Kondratenko. Introduction. The rapid advancement of artificial intelligence has ushered in transformative methodologies for biometric authentication. Among these, fingerprint-based security systems are both prevalent and effective. However, acquiring large, diverse, and privacy-conscious datasets remains a notable challenge. This research introduces an enhanced GAN framework employing gradient penalty mechanisms to synthesize realistic fingerprint images. The objective is to facilitate robust applications in both academic research and practical biometric systems. Background on GANs and fingerprint synthesis. Generative adversarial networks, or GANs, have proven pivotal in the domain of synthetic image generation. Within this paradigm, a generator fabricates images while a discriminator evaluates their authenticity. Initial architectures such as DC-GAN made significant strides but were hindered by issues like training instability and mode collapse, particularly in the intricate domain of fingerprint synthesis. The advent of the Wasserstein GAN with gradient penalty, or WGAN-GP, has substantially mitigated these limitations, enhancing both stability and output diversity. Proposed method: EA-DC-GAN. Our proposed model, termed Enhanced Adaptive DC-GAN or EA-DC-GAN, builds upon the foundational DC-GAN architecture. It introduces the Wasserstein loss function coupled with gradient penalty to ensure Lipschitz continuity, effectively countering mode collapse. Moreover, adaptive learning rates and the integration of instance normalization within the discriminator contribute to a stable and efficient training process, producing highly realistic fingerprint imagery in fewer training epochs. Model architecture. The EA-DC GAN comprises two primary components, the generator and the discriminator. The generator maps a latent noise vector into a high-resolution fingerprint through transposed convolutional layers, employing batch normalization and ReLU activations, finalized with a 10H output for pixel scaling. The discriminator leverages instance normalization and leaky ReLU activations, ensuring fine gradient preservation of rich detail and textural consistency. Model configuration. This slide details the specific configuration parameters employed in the model's implementation, each selected to optimize convergence and output quality. Training process. Training was conducted using a rigorously structured pipeline. Real fingerprint images were resized to a standard 128 by 128 resolution and normalized appropriately. The discriminator is trained more frequently than the generator, typically at a 5:1 ratio, ensuring robust learning of fingerprint characteristics. The model achieves convergence in approximately 200 epochs, a marked improvement over traditional approaches which require significantly more iterations. Experimental setup. Experiments utilized the SOCOFING dataset, a publicly accessible collection of fingerprint images. Data were standardized and processed in batches using PyTorch, with training executed on NVIDIA Tesla P100 GPU. Key hyperparameters included a learning rate of 0.0002, Atom optimizer with beta values 0.5 and 0.999, and carefully tuned gradient penalty coefficient. Results and analysis. The AADC GAN model consistently produced synthetic fingerprint images of high fidelity. Visual analysis confirmed the presence of coherent, rich structures and minimal artifacts. When compared with traditional DC GAN models, our framework demonstrated superior output diversity and training stability, attributes attributed to the introduction of gradient penalty and instance normalization. Real data. Shown here are samples from the SOCOFING dataset representing authentic input used during training. Synthesized samples after 10th and 20th epochs. These initial results illustrate the model's capacity to generate coherent structures within just 10 to 20 epochs, highlighting the training efficiency. As training progresses, the fidelity and detail of the synthetic fingerprints improve substantially. By epoch 200, the generated samples are virtually indistinguishable from authentic scans. Cybersecurity and biometric implications. The capacity to generate synthetic fingerprint data has profound implications. While it enables scalable and privacy-preserving datasets for research, it also raises security concerns, notably the potential for spoofing attacks. It is essential that we concurrently develop detection mechanisms capable of distinguishing between genuine and synthetic biometric inputs to safeguard the integrity of such systems. Conclusion and future work. In summation, the proposed EADC GAN framework offers a substantial advancement in synthetic fingerprint generation. By incorporating gradient penalty and instance normalization, we achieve superior image quality in fewer training epochs. Future work will explore higher resolution outputs, integrate quantitative evaluation metrics such as frechet inception distance, and develop spoof detection techniques to ensure practical applicability and security. Thank you for your attention.